The main force accounting for the fluid acceleration will be due to normal stresses, to pressures. All the experiments will be in steady flow. Our first experiments have to do with changes of pressure and velocity in the streamwise direction. Our first test section is a contraction of cross-sectional area. This is how it fits to the nozzle. Static pressure manometers are located at the upstream and downstream cross-sections. And now he has started the flow. We see that the pressure falls from the upstream section to the downstream section. What about the velocity of the flow? Since water is nearly incompressible, the volume flow entering the contraction must equal the volume flow leaving, or else mass would be created or destroyed. But the volume flow is equal to the average velocity times the cross-sectional area, so the area decrease should produce a velocity increase. The velocity increase in the contraction is coupled to the pressure decrease by Newton's law of motion. Let's see how. Here, the bubbles mark many streamlines. Let's imagine that this is a typical fluid particle. For thinking physically about the problem, it is helpful to use the streamlines S and the normal trajectories N as curvilinear coordinates. First, let's look at the forces and accelerations along S for the typical fluid particle moving with speed v along S. Here is the particle enlarged. Since there are no viscous stresses, the normal stress at a point is uniform in all directions. It is a scalar, which varies from point to point. The net force on the particle acting along S comes from the difference of pressure on these two faces to the pressure gradient, dP ds. The acceleration along S is related to the convective increase of velocity as the particle moves along S, and, in Eulerian description, is equal to v dv ds. From Newton's second law, force per unit volume equals mass per unit volume times acceleration, we get Euler's equation of steady motion along the streamline. This minus sign tells us that a velocity decrease in the streamwise direction is accompanied by a pressure increase. Or conversely, a velocity increase is accompanied by a pressure decrease. This is a manifold. The pressure distribution is shown by the water levels in these manometer tubes. With the bleed valves closed, the average water velocity is the same at all cross sections, and there is a very slight pressure drop due to viscous forces. I'll reduce the volume flow at successive sections by bleeding water from the manifold. The pressure now rises. Since the area is constant, the velocity is proportional to the volume flow. Therefore, the velocity decreases. It is this streamwise deceleration which produces the streamwise rise in pressure. In an incompressible, steady, non-viscous flow, Euler's equation has a special integral called Bernoulli's integral. Along each streamline, the sum of the static pressure and the dynamic pressure is a constant. This sum is called the stagnation pressure. On any streamline, where the velocity is high, the pressure is low, and vice versa. The highest possible pressure, the stagnation pressure, occurs where the velocity is zero. A very large reservoir supplying a flow to a duct system is itself a stagnation region. Here is a streaming flow past a blunt body with a central stream tube marked by hydrogen bubbles. The widening of this stream tube tells us that the flow is decelerating. The singular point where the central streamline reaches the nose is a stagnation point. The speed is zero there. On both sides of the unique stagnation streamline, the fluid decelerates, but not to zero speed, and then slides around the sides. The stagnation point is put to practical use in a pitot tube. The hole at the nose measures the stagnation pressure of the particular streamline reaching the hole. We've placed pitot tubes at the upstream and downstream cross-sections of the contraction, and these are the static pressure manometers we had before. The difference between the stagnation pressure and the static pressure is the local dynamic pressure. So this is a way of measuring velocity. Because of the area contraction, both the dynamic pressure and the static pressure change. But the sum of the two, the stagnation pressure, remains constant, which is what Bernoulli's integral told us. A great many static pressure taps are in the straight wall and in the curved wall. Here it is set up for test. These are inclined manometer boards to show the pressure distributions on the two walls. We will observe the lengths of the water columns looking down from a position directly above. Now the flow is steady. We will look first at the pressure distribution on the straight wall. Continuity tells us that because of the area contraction, the velocity increases to the throat, and this causes a pressure drop. Downstream of the throat, the area increase produces a velocity decrease, and this causes the pressure to rise. At the upstream and downstream ends, where the cross-sectional areas are equal, the average velocities are also equal, and Bernoulli's integral would predict equal pressures. But the downstream pressure is actually somewhat less than the upstream pressure. This difference is due to viscous boundary layers, whose behavior we must always keep in mind, even when we pretend viscosity is absent. For instance, the area divergence here is much too rapid, and there is very little static pressure recovery in the diffuser. Far less than before. Even a very small amount of viscosity, if it leads to boundary layer separation, can produce very large changes from a truly non-viscous situation. As we increase the flow, all pressure differences increase with the square of the velocity, and the pressure at the throat decreases. The gauge shows vacuum, and the pressure at the throat is now about 20 inches of mercury below atmospheric. Watch the throat. These patches that form are actually steam. This is cavitation. When the absolute pressure goes below the vapor pressure of about 1 inch of mercury, boiling occurs. The water changes to steam, and the subsequent collapse of the bubbles, which you can hear, creates enormous stresses in the wall. Mechanical stresses owing to the implosive collapse of cavitation bubbles on a surface do great damage to hydraulic machinery. And to marine propellers. We've discussed the relation between pressure and velocity changes along the streamline. But see how different the pressure distributions are for the two walls. To understand this, we must now think of the particle dynamics normal to the streamlines. This again is our system of streamline coordinates. At this point on the particle trajectory, the radius of streamline curvature is r. The net pressure force acting toward the center of curvature is due to the difference of pressure on these two faces, to the gradient dp dn. Although there is no velocity along n, there is an acceleration, v squared over r, toward the center of curvature. Setting force equal to mass times acceleration, we get Euler's equation of motion normal to the streamline. Here, the important thing is curvature of the streamline. The pressure always increases outward from the center of curvature. In this bend, the streamlines are curved. This is a set of 3 static pressure manometers in the straight section approaching the bend. This set is in the middle of the bend, and this set in the straight section following the bend. In the upstream straight section, the streamlines are virtually straight, and the 3 manometers show no pressure variation normal to the streamlines. This tall tube shows the stagnation pressure in the large upstream settling tank. The difference between this stagnation pressure and the static pressure at the upstream tubes gives a dynamic pressure of about 11 inches of water. At the middle of the bend, there is a pressure difference normal to the streamlines of about 3.5 inches of water. This is close to what we would predict using Euler's equation for the normal pressure gradient. Downstream of the bend, the pressure is almost uniform again. The slight variation there is due to a complicated secondary flow induced by the bend. As we increase the flow, all the pressure differences also increase, according to the square of the velocity. But the pressure difference due to curvature remains a constant fraction of the dynamic pressure. The throat pressure at the curved wall is considerably less than at the straight wall because of the streamline curvature. When we use Venturi's for flow measurement, the pressure we measure at the wall is therefore not the average pressure at the throat. That is one reason for calibrating Venturi meters. So far, we've looked separately at the pressure gradients along and normal to the streamline. To understand a complete flow pattern, however, we must consider both of these. And of course, we must also consider the equation of continuity to ensure that mass is conserved. Our flexible wall rig now is in the form of half of a rapid symmetrical contraction. Upstream, the pressures are equal on both walls. Downstream, they are also equal, but lower. Because of the area decrease, the average velocity increases, and, according to the streamline's equation of motion, the average pressure falls. On the straight wall, the pressure falls continuously, but on the curved wall, it first rises, then undershoots to a very low pressure before reaching its final value. Here are the pressure distributions superposed. Let's see how these pressure distributions may be predicted by the two dynamical equations and the equation of continuity. This curve of pressure versus distance shows the average streamwise pressure variation associated with the one-dimensional average velocity at each cross-section. Far upstream and far downstream, where the streamlines have no curvature, the pressure will be uniform over the two cross-sections. From the shape of the channel, we may expect that the streamlines will be of this general shape: concave up in this region, concave down in this region. These are two curves normal to the streamlines in the regions of different concavity. And these are the directions of increasing n. That is, outward from the center of streamline curvature. From a one-dimensional point of view and a comparison of cross-sectional areas, we may expect the average pressure on AB to be only slightly less than the upstream pressure. But because of streamline curvature, the pressure increases from A to B, so that the pressure at B will be greater than the pressure at A. Similarly, the average pressure on CD will be only slightly greater than the downstream pressure. Again, though, because of streamline curvature, the pressure will increase from C to D. So the pressure at D will be greater than the average, while the pressure at C will be less than the average. So the pressure on the curved wall rises to a maximum at B and then falls to a minimum at C. While on the straight wall, it falls continuously from A to D. According to Bernoulli's integral, which in this case has the same value for all streamlines, the velocity is a minimum where the pressure is highest, and it is a maximum where the pressure is least.